This is section 6.9, and we're going to talk a bit more about specifically exponential growth. And as you already know, that means we'll be using logarithms as well. So we'll be using the functions that we kind of talked about the calculus of in the last section. Of all the sections that we do this semester, this one is likely to feel the most familiar. A lot of the skills that we'll be covering in here are very similar to or just slight extensions of things that you probably have learned in college algebra and pre-calculus as well. All right, we're going to start by talking about the difference between the absolute and relative growth rates. The absolute growth rate is what we've just been calling the rate of change of the function, and that's going to be the derivative. We're changing over time. We'll assume it's a function of t, so we'll call it y prime of t. The relative growth rate is that absolute growth rate divided by the current value of our quantity, so y prime divided by y itself. Let's compare absolute and relative growth rates for linear and exponential functions. If we've got a linear function of the form f of t equals mt plus b, then our absolute growth rate or derivative is just going to be m. The relative growth rate, f prime over f, would look like m for the f prime, and then the whole function mt plus b for f itself. So we'll note that for a linear function, the absolute growth rate is going to be constant. All right, what about an exponential function? Basic form for an exponential function we'll use is c e to the kt, c and k being constants. So our absolute growth rate, y prime of t, would be the derivative, c times e to the kt times k with our chain rule, or ck e to the kt. And then the relative growth rate is going to be y prime divided by y. So I'll take the y prime from up here, divided by the original function, which was c e to the kt. And of course we get a lot of things that divide out here, the c's, the e to the kt's, and that simplifies to just k. So the relative growth rate for our exponential function is constant. All right. Let's take a look at a few exponential growth functions. Start talking a little bit about things that we can do with them. In general, exponential growth is described by a function of the form y of t equals y naught e to the kt, where the initial value of y at time 0 is denoted as y naught, and then the rate constant k is positive, and that determines the rate of growth. We are specifically talking here about growth functions for the moment. Exponential growth, remember, is characterized by that constant relative growth rate. And that's what our rate constant is going to end up telling us. So, suppose that we have a population, two towns actually, the town of Pine, given by this linear function, and the population of Spruce, given by this exponential function, for t is greater than 0. And we'd like to find the growth rate, and when I don't say anything, I'm assuming absolute growth rate, and then also the relative growth rate of each town. So let's see here for Pine. We'll start with our absolute growth rate. And let's see, that would be our derivative, p prime, so 125. Constant, since that was a linear function, that's not a surprise. And if I had to put units on this, let's see here. T is measured in years, so population would be changing at the rate of 125 people per year. All right, what about the relative growth rate? This is going to be p prime divided by p. So we already know p prime, that was 125, divided by the original function for p itself, 1500 plus 125t. Of course, that's not constant. That's going to depend upon time. And just notice the units on this. The p prime was in people per year. The population itself is going to be people. So the people divide out. And I know it's going to sound a little strange, but the units on the relative growth rate are just per year. There's no units left on the top, right? The people have already canceled out. So literally it's this value per year. And that's characteristic of relative growth rates. Their units are just going to be per whatever time unit we have. All right, so let's do the same analysis for spruce. The absolute growth rate is just the derivative. And for spruce, that would be 1500 e to the 0.1 t, and chain rule times 0.1, giving me 150 e to the 0.1 t. And once again, that's just the derivative. That would be in people per year. That's not constant. It depends upon time. And then our relative growth rate, s prime over s. We'll take our s prime from here. Divided by the original s function itself. And of course the exponentials will divide out. 150 divided by 1500 is going to be a tenth, or 0.1. And again, not surprisingly, that growth constant, 0.1, is actually our relative growth rate. And I'd say 0.1 per year. It sounds a little funny, so oftentimes when it's constant, we change it to a percentage and call it 10% per year. And that's fine as well. So, when we think about our growth rates, the slope is the absolute growth rate constant for a linear function. The k value is the absolute growth rate, or the relative growth rate constant for an exponential function. Okay. All right. Sticking with the theme of population, let's take a look at example 2. Human population growth rates vary geographically and fluctuate over time. The overall growth rate for world population actually peaked at an annual rate of 2.1% per year during the 1960s. Assume that a world population was 6 billion in 1999, we'll consider that our time zero, and that it was then 6.9 billion in 2009, which would be 10 years later. I would like to find an exponential growth function that fits that decade for the world population. And again, it has to fit those 2 data points. Just to organize my thoughts, I kind of like to make a little chart, little table. At time 0, we had 6 billion. And at time 10, the population was 6.9 billion. Now we want our population equation to fit this exponential model that we're using, which was y equals y naught e to the kt. In our case, instead of y, we've got p. So I'll just call that P equals P naught, e to the kt. And we already know P naught. At time 0, there were 6 billion people. So I can plug that in right away. And then, assuming that I'm supposed to be doing this by hand, obviously if I could use a calculator or Desmos, I could just run a regression, but we're going to go ahead and do it by hand. I'm going to take the second point from my table and plug in the time 10 and the population of 6.9. And that's going to allow me to solve for the growth constant, the k value. Let's see, if we divide by 6, we get 1, what do we get? $1.15 equals e to the 10k. Got to get rid of the e, so I'll do that with the inverse function, the natural log. And so dividing by 10, I'll have 1/10 times the natural log of 1.15 is the k value. Now we could put that in the calculator and we could get a decimal approximation for that. And as a matter of fact, if we want to kind of get an idea of what the percentage per year is, we might want to do that. But in order to keep my actual equation, my exponential growth function, as accurate as possible, I'll typically just leave the constants with a natural log in them. So I'm going to say here, my growth equation would be P equals, the P naught was 6, e to the ln 1.15 over 10 t. The advantage of doing that is if I were to use a very large t value, let's say I wanted to predict what was going on like 1,000 years later or something, if I've used a rounded decimal, multiplying it by a large t value will cause a great deal of round-off error, whereas if I've kept the exact value in here, it doesn't matter how big t is, I'll still be able to get a reasonable result. So this is how I'm going to write my exponential growth equation. If I'd like to have an idea of, well actually we'll go ahead and do that over here. Next we're supposed to find the absolute and then the relative growth rates. So the absolute growth rate is the derivative, p prime, and I'll just tuck this up here so we can see our population equation while we're working. The derivative would be 6 times, and of course the derivative of the exponential is just going to be itself, and then the chain rule here, derivative of the exponent would be the natural log of 1.15 over 10. That's our absolute growth rate. It does depend on time. It is certainly not a constant. What about the relative growth rate? That's p prime divided by p. So I'll take everything I got up here, and I'll divide by the original population equation. And that's going to allow me to divide out all of this with all of that. Oops, missed a t here, sorry. And so I end up with just this. And I'm going to go ahead now and I'm going to put that value in my calculator. And let's see, what am I going to get? The natural log of 1.15 divided by 10 gives me about 0.014 if I round off to 3 decimal places. This is now rounded. So my relative growth rate is 0.014 per year. Or if I change that to a percent, I could say 1.4%. per year. Notice that's definitely down from that peak value of 2.1% per year that the problem told us was occurring in the 1960s. All right, next thing we want is the doubling time for the world population using our model. So, again, my population model was 6e to the natural log 1.15 over 10 times t. And if I'd like to know the doubling time, I literally want to know how long will it take for the population to double under these circumstances. Since my initial population was 6, doubling is going to be 12. So let's see, we'll divide both sides by 6 and get 2 equals this exponential. And in order to solve for the t, I'd like to get rid of that e. So actually, I'm just going to sneak it in so I don't have to keep writing this so many times. Let's do a natural log on both sides. Gets rid of the e over here. And so if I have the natural log of 2, I'll divide it by that value to get t. And I just went ahead and put that into my calculator, and I got about 49.5 years. So this population is going to double about every 49.5 years. All right, last question for this particular example. We'd like to know how fast the population was growing in 2014. Notice that is 15 years after 1999. Right? Now, I didn't say whether I wanted the absolute or relative growth rate, so we'll go ahead and give both. The absolute growth rate is just p prime. And we had that up at the top of the page, right? We had it right up here. So I'm just going to go ahead and take this absolute growth rate right here, and I'm going to plug in my t equals 15. And I won't write that all out. I'll just say if we plug 15 in there, put everything into the calculator, I ended up getting about 0.104. And that would be in billion people per year. The relative growth rate that's p prime over p. And that one we did in part C. Right? And it actually didn't matter what the time was. Everything canceled out, and we ended up with a constant, as we always do for exponential functions. So we already know it was just 0.014 per year, or 1.4% per year. So depending on whether that problem meant absolute or relative, I would answer it a little bit differently. All right, our next problem is going to be looking at a financial application. Exponential functions are actually used a lot in financial applications because when you have something that pays interest, interest is a percentage of your deposit, meaning that we've got a constant relative growth rate and therefore an exponential function. In all cases, the balance in the account then increases exponentially at a rate that can actually be determined, if this is a deposit in a bank account, from what the bank advertises, which is not actually its growth rate. Banks always advertise their annual percentage yield or APY. We can use that value to actually calculate the constant growth rate, but it'll be a little bit different than this APY. We're going to do an example, and then we'll talk about why we think banks prefer to advertise the APY rather than the actual annual growth rate. So here we go. In our first problem, the APY, or annual percentage yield of a savings account, is defined as the percentage increase in the balance over the course of 1 year. Let's suppose you deposit $500 in a savings account that has an APY of 6.18%. Assume the interest rate remains constant. We don't make any extra additional deposits or withdrawals. My question is, how long will it take the balance to reach $2,500? Well, in order to answer that question, I'd really like to come up with a model for the amount in the account. And in order to do that, I'm going to say, all right, the amount in my account should be able to be modeled as A0, the initial amount, times e to the kt. That's a typical exponential growth function, right? Here we're using y. I'm just choosing to use a for amount. We do know the initial amount in the account is $500. That's what our deposit was. So I know the A0 is 500, and I can put that in right away. Now, just like the last problem we did, we need to figure out K. So in order to do that, I'm going to use this information about the APY. I know that in 1 year, so t equals 1, the account grows 6.18%. That's what APY means. So that tells me that my $500 times a 6.18% growth rate would be 1.0618, right? That's the 6.18% plus all of what I started with is going to give me, excuse me, 1 second, get a little dark here. I gotta hit some light so I can see my calculator. That means that I'm going to have 500 times 1.0618, $530.90 in the account after 1 year. I'll take that information. This is my T. This is my A. I'll plug it in here, and that's going to allow me to solve for the K. So 530.90 equals 500, e to the K times a time of 1 year. If we divide out the 500, not surprisingly, I get 1.0618 equals e to the K. And we'll just take the natural log of both sides. Again, I'll sneak that in here to get rid of the e. And K is the natural log of 1.0618. I'm going to give myself an approximation for K right now, just because I want to point out to you why banks advertise the APY rather than the actual growth rate, or the growth constant. If I take the natural log of that value, this is about 0.059966, or about 0.06. What that tells us is the actual growth rate of the account is about 6% per year. When we define growth rate the way mathematicians do for an exponential function. Of course, it sounds better to say the APY is 6.18% than to advertise the 6%. So banks tell you, hey, this is what you'll get if you keep your money in here for a whole year. The 6%, however, is a more accurate reflection of the constant growth rate that you're actually experiencing. All right? Okay, so that's true, but I am going to keep this exact value in my equation. So I'm now going to write A equals, the A0 was 500, e to the ln 1.0618 for k times t. And the question was, how long will it take the balance to reach $2,500? So I want to know, when will there be $2,500 in the account? If we divide out the 500, we'll get 5. And once again, to get rid of that e, I'll just take the natural log on both sides. So I have natural log 5, and I'll have to divide by the natural log of 1.0618 to get the time. And that came out to about 26.84. So, if you don't need that $500 and you can leave it in there for almost 27 years, you will quintuple your money at that growth rate. All right, our next example is an example that has to do with energy consumption. I'm going to kind of read this together just because there's some interesting information that may not be common knowledge. I know it really wasn't to me until I read it, so let's take a look at this together. Among many resources that people use, energy is certainly one of the most important. Our basic unit of energy is called the joule, and that's roughly the energy needed to lift a 0.1 kilogram object, like an orange, a meter. The rate at which energy is consumed is called power. And the basic unit of power is the watt. 1 watt is 1 joule per second. In fact, if you turned on a 100-watt light bulb for 1 minute, the bulb consumes energy at the rate of 100 joules per second, and it would use a total of 100 joules per second times the 1 minute, or 60 seconds, or 6,000 joules of energy. Now, when you think about that being how much energy it takes to run a 100-watt light bulb for 1 minute, you can appreciate the fact that measuring our energy consumption in joules is not realistic. That's going to be huge numbers. So we need a more useful measure. And that more useful measure of energy for larger quantities, which we would all be consuming, is the kilowatt hour, kWh. A kilowatt is 1,000 watts, or in other words, 1,000 joules per second. So this would have been 6 joules, or 6 kilowatts, rather. If you consume energy at the rate of 1 kilowatt for 1 hour, 3,600 seconds, you've used a total of 1,000 joules per second for 3,600 seconds, or 3.6 times 10 to the 6th joules. And that's defined as 1 kilowatt hour. So instead of having these huge numbers, we've now made a new definition. That's just one of these new units, the kilowatt hour. Again, just for reference, a person who runs for an hour consumes roughly 1 kilowatt hour of energy. Typical house uses on the order of 1,000 kilowatts hours of energy in a month. That's what you actually see on your electric bill, how many kilowatt hours you've used, and that's how the electric company charges you, based on the number of kilowatt hours. All right, here we go with the math now. Let's assume that the total energy used by a person or machine or a city is given by the energy function, E of t. Since power is the rate at which energy is used, power is going to be the derivative of energy, right? Rate of change, derivative. Using the ideas then from back in section 6.1, the total amount of energy used from time A to time B would be the integral of E prime, or in other words, the integral of the power function from time A to time B. That means that energy is actually the area under the power curve. With that background, we're going to go ahead and look at our next example. So here we go. At the beginning of 2010, the rate of energy consumption for the city of Denver was 7,000 megawatts. 1 megawatt is 10 to the 6th, or 1,000,000 watts. That rate is expected to increase at an annual growth rate of 2% per year. Okay. Find the function that gives the power or rate of energy consumption for all times after the beginning of 2010. All right, so here we go. First of all, we need to find the function for power. And hang on one quick second here. Sorry about that. All right, so let's see. We know a few things. First of all, we know the rate, that is the power function, is expected to increase at an annual growth rate. Notice annual growth rate. This is like the APY. It's annual. It's not the continuous growth rate. It's the annual growth rate. And we also know that at the beginning, we'll call t equals 0, the year 2010. So when t equals 0, we know that the initial power, P naught, was 7,000 megawatts. So let's see if we can use that to come up with a power or rate of energy consumption function. So I'm going to say power P equals P naught e to the kt. P naught is that 7,000 in the year 2010. And then we also know that we get an increase of 2% per year. So when t equals 1 year later, the power is going to be the original 7,000 times an increase of 2%, so times 1.02, or 7,140. So let's put that in. 7,140 equals 7,000 e to the k times 1. 7,140 divided by 7,000, of course, is going to give us our 1.02 back again. And that's just going to equal e to the k. In order to solve for k, all I need to do is take the natural log of both sides. And so k is the natural log of 1.02. By the way, the natural log of 1.02 is about 0.0198, so just a little bit less than 2% for the actual continuous growth constant k. But I'm going to leave the exact value, natural log of 1.02. So my power function is 7,000 e to the natural log 1.02 t. Again, always better to use the exact value of the equation. That way you don't end up with a bunch of round-off error because you didn't keep enough decimal places. All right, we now want to find the total amount of energy used during 2014. So if we think about from the start of 2014 till the end, or in other words, kind of like the start of 2015, this would be from t equals 4, that would be the beginning of 2014, to t equals 5, which would be the beginning of 2015. So that's a 1-year span in there. Energy, right up here, right, is the integral of the power function. So we're going to integrate this p function. From 4 to 5. Okay. I just went ahead and did that on my calculator, and I got 7652.54, oh, excuse me, yeah, 0.5453. Let's think a little bit about the units on that. Because this was in megawatts, right? This is not going to be megawatt hours. This is going to be, this is not going to be kilowatt hours. This is going to be megawatt hours. And as a matter of fact, it's not even going to be hours, is it? These are in years. Just realize that. So this is megawatt years. Not our usual units. If we actually wanted to convert this to kilowatt hours to see what the city of Denver is using in that year and think about what their electric bill might be collectively, we could actually convert our 7652 megawatt hours, or megawatt years rather, into kilowatt hours. That's megawatt years. Let's see here. Kilo is 1,000, mega is 1,000,000, so there would be 1,000 kilowatts in 1 megawatt. Gets rid of our megawatts. I don't want years, I want hours. I know that 1 year is 365 days. Gets rid of my years. I know that 1 day is 24 hours. Gets rid of my days. And I know that 1 hour is 3,600 seconds. Gets rid of my hours. So there we go. I now have left kilowatt. Oh, wait a minute. I went hours, not seconds. I went 1 too far, didn't I? Sorry about that. I was really getting into this. Let's get rid of that last part. We won't do that. We'll keep the hours. That'll be kilowatt hours. When I multiplied all of this together, I ended up getting 6.7 times 10 to the 10th kilowatt hours, or kWh. So if you want to pay the city of Denver's electric bill, that's how many kilowatt hours you would have had to have paid for back in the year 2014. An answer like this, of course, is just fine. It's in the units that were given. I just thought it would be interesting to see what would happen if we changed to the more familiar kilowatt hour units. All right, the next question, also kind of a reminder of what we did back in 6.1. We'd like to find the function that gives the total or cumulative amount of energy used by the city between 2010 and any time t greater than or equal to 0. 2010 being our t equals 0 year. Right? This, what we're really being asked for, is that future value equation. The value in the future for any time t greater than or equal to 0. So the total amount of energy is the integral of the power function. Only this time I don't have limits of integration because I want it to be general for any time greater than 0. And so I would have the integral of 7,000 e to the natural log 2 times t dt. I can pull the 7,000 out of the integral. And then I have to use a little u substitution here. U would be ln 2 times t. So du would be ln 2 dt. And du over ln 2 would be dt. That's going to make this e to the u. And I'll replace the dt with du over ln 2. Integral of e to the u is e to the u. And I'm going to go ahead and put that u back in, like so. And there's my constant of integration plus c. Now, I can solve for the plus c by using the fact that right at the beginning, in 2010, at the very beginning, we've used no energy, right? 2010 was the starting point. So I can say that at T equals 0, the total energy used is 0. So plugging that in, I would get 0 for energy equals 7,000 over ln 2, and that'll just become e to the 0 plus c. E to the 0, of course, is 1. So c is negative 7,000 over ln 2. And my final energy equation at any time t would be 7,000 over ln 2 e to the ln 2t minus 7,000 over ln 2. All right. One more example, or one more type of example. We're going to be looking at exponential decay functions here. And the only difference between an exponential growth function and an exponential decay function is in a decay function, the growth constant is always going to be negative. So we'll think of it as y equals y naught e to the minus kt. We still have our initial value at time 0. That's what the y naught is. And the rate constant k itself is greater than 0, determines the rate of decay. The negative is actually part of the function itself. So exponential decay, we're going to have a constant relative decay rate. All exponential functions have constant relative rates of change. And one really helpful little equation for these is this little equation about the half-life. So often with exponential decay functions, we talk about the half-life, which is simply the amount of time it takes for half of whatever we're using to be gone. So the amount of time for half of y to, I'm just going to say go away. Total amount gets cut in half. Right? The half-life is related to the decay constant by this little equation here. This is a really helpful one. We're going to use it a lot. T sub 1/2 is our half-life, and that's equal to the natural log of 2 divided by k. All right, keeping that in mind, let's take a look at this next example on radiometric dating. One method to estimate the age of ancient objects like rocks, bones, meteorites, etc., relies on radioactive decay of certain elements. One common version, and this is only useful to date things that used to be alive, like the bones of an animal, won't work for a rock or a meteorite. But what we do is we measure the amount of a certain carbon isotope called carbon-14 that's present in all living matter. When the living organism dies, the C14 doesn't get replaced. It experiences exponential decay. So by measuring how much C14 is still present, we can figure out how long ago that particular organism died. Okay? The half-life of carbon-14, the T1/2, is 5,730 years. So keeping that in mind, let's take a look here at example 5. Researchers have determined that a fossilized bone has only 30% of the carbon-14 of a live bone. Estimate the age of the bone, assuming the half-life of C14 is 5,730 years. So the first thing we're going to need is to write down our exponential decay equation. And I'm going to say, let's see, since we're talking about carbon-14, I'm going to go with C equals C naught. And this will be e to the minus kt. Since we do have decay, we know our exponent's going to be negative. And I have a nice easy way of determining the k value this time because I have that half-life equation. Right? First of all, C naught, we'd start with 100%. So C naught's 100. We then have our half-life equation. T sub 1/2 is ln 2 over k. They told us the half-life, 5,730 years. And so we can just use that little equation to solve for k. K would actually be ln 2 divided by 5,730. So that means I can write my decay equation as C naught, which we've decided is 100, representing 100%, e to the negative ln 2 over 5,730 times t. My goal now is to find out the amount of time, the age, so I want t, if the sample that we have only has 30% of what the carbon-14 in a live bone would have. So instead of 100%, I now have 30%. If we divide by 100, we're going to get 0.3. And once again, I got to get rid of that e, so let's just take the natural log of both sides. And I'd have the natural log of 0.3 divided by minus ln 2 over 5,730 is equal to t. And just plugging that in the calculator, I got 9,952.8 years. So almost 10,000 years old for this particular sample. In addition to things like isotopes or radioactive elements decaying, another really common example where we use half-lives and exponential decay is in the medical fields. When you take a medication, the way that that medication leaves your body is by a process that's governed by exponential decay. The formal name for this is Thermokinetics, the movement of medication. It describes the process by which drugs are assimilated by the body. The elimination of most drugs from the body can be modeled by an exponential decay function with a known half-life. By the way, one thing that doesn't work with this model actually is alcohol. Here's some half-lives for common medications. Half-life for penicillin is an hour. Half-life for nicotine is 2 hours, and so on here. The simplest model, which is what we're going to use here, is going to assume that the entire drug dose is immediately absorbed into the blood. We know, in fact, that unless it's an intravenous drug, that's actually an idealization. If we had a more refined model, we could actually account for like swallowing a tablet or smoking a cigarette or whatever and slowly absorbing the drug. But we're not going to go there in this course. We're just going to assume it's all available right away. And then the exponential decay governs the way that it's eliminated. So here we go. Exponential decay function models the amount of the drug in the blood t hours after an initial dose of 100 milligrams is administered. If the particular drug we're talking about has a half-life of 16 hours, first of all, let's find our exponential decay function. So y equals y naught, e to the minus kt. The initial amount was 100, so I know right away y equals 100, e to the minus kt. To solve for k, I can go back to that half-life equation again. The half-life is equal to the natural log of 2 over k. And if this half-life is 16, then k would be the natural log of 2 over 16. So my exponential decay function is 100 e to the negative ln 2 over 16 times t. All right, we now want to know how much time is required for the drug to reach only 1% of the initial dose. 1% of 100 is 1, of course. So we want to know how long it's going to take for there to be 1 milligram left. And let's see, if I divide by 100, I'm going to get 0.01. I need to get rid of the e's, so we'll take the natural log on both sides. So I have the natural log of 0.01 divided by the negative ln2 over 16 is t. By the way, one thing, I guess I haven't been doing this on screen, do be a little bit careful when you enter this in your calculator. If you've been having trouble getting the same values I'm getting, probably is because of how you're dealing with your parentheses. Remember that the calculator automatically puts the argument of the log in parentheses. So you're going to have the natural log of 0.01 in parentheses, and the natural log of 2 is going to be in parentheses. When I write them, just because it's a little bit ugly with all those parentheses, I often don't bother. But when you put it in the calculator, it'll have to be there. So if I take the natural log of 0.01 and divide by negative, actually, let's use let me find, let's use a parenthesis here. Negative natural log 2, parentheses, over 16, and then end my denominator. I get 106.3 for t. And this was all in hours, so it's going to take 106.3 hours for the amount of this drug to be reduced to just 1% of the initial dose. All right, that brings us to the end of section 6.9.